the first you are thinking of, the most beautiful equation, which symbolizes ordering, rigidity, simplicity, inevitability. Which equation would it be?
I guess it would be the equation I write down for my students in Physics 1. F equals ma. Couldn't be simpler mathematically. Of course, you have to define your terms, and when you, which is a pity.
So,
Too bad.
What are you writing down?
I'm telling you simply the following: that if you push on something, it's going to respond by moving. That's all. How hard do you push? How much will it respond? And yet, it covers so much of our world. How a rock rolls down a hill. How in the collapsing of dust clouds do you collect a certain amount into a spherical, roughly spherical accumulation of stuff, which we call a planet. And why water, when it falls out of a faucet, collects in a drop, which is spherical. And again, why, if we have a moon and a sun, we get tides? And why is it that the Earth bulges at the equator a little more than everywhere else? And, you know, why when you hit a billiard ball with a stick, it rolls and does all the tricks that a clever billiard player can demonstrate? All these things, everything, all comes out of that little equation. F equals ma. Force equals mass times acceleration.
That's beauty.
That's beauty. Power, beauty, power, empowerment. It empowers humans to control what they understand. I remember, going back to the Impressionist, rather famous painting of Gauguin, Tahiti. It was showed two Tahiti, rather beautiful Tahiti natives carrying fruit. There were mangoes. It said Tahitis with mangoes, but they were undressed up above, and I didn't know what mangoes meant, so I had the wrong impression about that word for a while. That's both beauty and consolation.
Please read.
Oh boy.
You know what I mean, what I'm talking
I
about.
don't know which one. The hero, oh, this is my last scene in the movie. The hero is the president of the Astrophysics Society, the only person ever to win 3 Nobel Prizes. He stands at night on the beach, legs planted wide, shaking his fist at the jeweled blackness of the sky, anointed by his humanity, aware of mankind's most powerful achievements. He shouts at the universe above the sound of the crashing waves. I have created you! You are the product of my mind. My vision, my invention, it is I who provided you with reason, with purpose, with beauty. Of what use are you but for my consciousness and my construction, which have revealed you? A fuzzy, swirling light appears in the sky, and a beam of radiance illuminates our man on the beach. To the solemn and climatic chords of Bach's B minor Mass, or perhaps the piccolo solo of Stravinsky's Rites, the light of the sky slowly configures itself into her face, smiling, but with an expression of infinite sweet sadness. Fade to black, roll the credits. Gee, did I write that? Wow.
We treden binnen in de tempel van de hedendaagse natuurkunde. Het hoofdgebouw van het Fermi Laboratorium. Op de bovenste verdieping, rechts, zullen we praten, met uitzicht op de prairie. Heb ik hem uitgenodigd omdat hij volgens vriend en vijand de experimenteel natuurkundige is van de afgelopen eeuw. Omdat hij 1 Nobelprijs kreeg, maar genomineerd had kunnen zijn voor nog 4 andere. Het klinkt overtuigend, maar 2 andere redenen waren minstens zo belangrijk. Als er een geboren leraar rondwandelt op aarde, dan is hij het. Luister naar Lederman, als hij je de raadselen van tijd, ruimte en materie uitlegt. En voor je het weet, word je meegesleurd in een wereld die je eerder volstrekt ontoegankelijk leek. Een geboren leraar met een bevrijdende humor en zelfspot. De briefwisselingen vooraf waren niet zelden hilarisch.
I quote you a letter last year. Okay, I will sit, stand, lie in front of your cameras and look up at the cosmos, down at the quarks, and look upon myself and curse my fate.
Yeah.
Wow.
We used to have to memorize Shakespeare's sonnets and things.
I curse my fate.
Yeah.
What did you mean?
Well, it's a quote. I mean, when in despair with heaven and men's eyes, I all alone beweep my outcast state, and trouble deaf heaven with its ceaseless cries. Look upon myself and curse my fate. You know, it's always a part of being sorry for yourself. You can do better. The desire to do better in almost anything is always there. You know, I think maybe it's a characteristic of science, but I don't think so. I think anybody who tries hard to do something that has never been done is never satisfied, except in maybe he or she allows themselves some moments of satisfaction, but often not. Often when you find in your work you're continuously driven. So, you know, standing still and you know, crying is okay.
De mango's van de Gauguin-meisjes. Dit uitzicht, aan de andere kant van het gebouw, op de gracht met een doorsnede van 1 kilometer, waaronder de deeltjesversneller loopt. Het lachje van Lederman. Waaruit is dit alles gemaakt? En volgens welke wetten? F is ma. De kracht is gelijk aan de massa maal de versnelling. Misschien is een mogelijk thema de vraag: waarom vragen we eigenlijk waarom? Opperde Lederman vooraf. Waarom denken we dat het heelal een oorsprong heeft? Waarom denken we dat het een doel heeft? Waarom denken we dat wij dat doel zijn? Ooit bewees hij dat het heelal niet symmetrisch is. Godzijdank. Anders had hij me vandaag niet kunnen ontvangen.
And that's something I can explain too. It's not so hard to see. In the beginning, we had lots of energy, and in the, you know, say now the world has been born. You know, a billionth of a billionth of a billionth of a second ago it was created, and we have the soup of primordial particles smashing into each other with unbudgeted energies. There was no budget in those times. They had all infinite amount of money to make all the particles they wanted to make. And energy was converted to particles and antiparticles, and antiparticles and antiparticles annihilated to make energy. And there was this going back and forth and cooling and expanding. There was this hot primordial soup of things going on. Now, if in fact there was perfect symmetry, then matter and antimatter would be present in equal numbers. And as the universe expanded and cooled, the matter and antimatter would eventually all eat each other up and make energy. But the energy would then be too impotent as it got cool to make matter and antimatter. So ultimately, all the matter would be converted to energy, and we would have a universe consisting of pure radiation. We'd have lots of light, but we'd have no things, no rocks, no stones, no fishes, no humans, no movie stars, nothing. We'd have only radiation. So CP, the violation of CP, became a very significant and profound thing. It enabled a little bit of asymmetry to be left over when all the matter and antimatter are annihilated. And that little bit of leftover matter is us, sitting here talking about it.
That's beauty.
So that's...
Isn't that beauty?
It is. It's incredibly beautiful and somewhat consoling.
Consoling, I don't know.
Well,
beautiful it is.
Yeah.
Consoling?
Sure, because it, I mean, there may be. I mean, there's a model which says that lots of universes were tried. And if universes were tried and somebody forgot about the fact that CP can't be a perfect quantum number, you'd have a pretty boring universe.
We are sort of left over.
That's right, we're left over.
And that enables that we are talking here with a wonderful view on the prairie.
Isn't that consoling?
That's consoling.
My amazement, I remember once reading a book which had to do with how Niels Bohr solved the problem, or at least to his satisfaction, in 14, 15, of the spectra. Mm-hmm. You know, if you heat up metals, they glow with various characteristic colors, and if you examine these colors in quantitative detail, you see very sharp spectral lines. Mm-hmm. I mean, color has numbers. Red is 5,900 angstroms, and deeper red is 6,200 angstroms. But what you really see when you look at these metals are very sharp lines at 5,922 angstroms, and those are spectral lines. Yeah. And every chemical element leaves its fingerprints, if you like, its characteristics in a series of lines. And one could measure where these lines are and write down a little formula, which then would predict where the next lines are. Some of them are in the blue, some of them are in the red and in the yellow and so on, and some of them probably are in colors we don't see with our eyes, like infrared, ultraviolet. These spectral lines have been around all through the 19th century with increasing precision. There were books of these spectral lines. So if you wanted to know about the element sodium, you could look up the spectrum of sodium. It was sort of the fingerprints of that element. In fact, the element helium was discovered in the sun and looking at the light of the sun before it was discovered on Earth. That's why it got the name helium, from sun. Bohr found a way of understanding these spectral lines by just considering the structure of an atom. An atom, he reasoned, is filled with electric charges, and in the early 1900s, we understood that these charges the positive charges were concentrated into a minuscule nucleus and a cloud of electrons outside the nucleus. And Bohr thought of these electrons as in orbits, very much like the orbit of the Earth around the sun. But then he devised a way of treating these orbits, and he called these electrons orbital jumps, where an electron would jump from orbit 1 to orbit 2, and in that jump would emit a characteristic spectral line color. And he wrote down a formula which had in it the charge of the electron, the mass of the electron, other characteristics, the speed of light, things that looked irrelevant. And when these numbers, these letters were jumbled together to make his formula for the spectral lines, and you put in the values that were known for the charge of the electron, the mass of the electron, and so on, out came the spectrum of sodium or helium or hydrogen. Actually, it was hydrogen that he did analyze. And that was very exciting. How could you explain the colors of light by just talking about these little, abstract things that we can't even see, these electrons? And somehow, all of a sudden, the notion had a reality to it. Now, I must have been early high school when I read this, and I just couldn't sit still. I put the book down. I was alone in my house and walked up and down through the rooms, being so excited by this particular triumph, which turned out to be the beginnings of the quantum theory, called the old Bohr theory. Not old Bohr, but Bohr's old theory. And for me, the intriguing thing were the particles. I remember reading the award of the Nobel Prize to Carl Anderson for discovering the positive electron, and how he had carried a device called a cloud chamber to the top of a mountain to study the cosmic rays. To me, that was real adventurous. That was Indiana Jones. I didn't know about Indiana Jones, but it was like that, you know.
Yeah.
Not only were you on the track of these mysterious particles, but you were doing something glamorous, like getting up to the tops of inhospitable mountains and setting up your apparatus, and all sorts of difficulties. No electricity, no running water. You had to run your own cables. That was good stuff.
Did you visualize the particles? Did you see them? Did you have any relationship with them, or were they just abstractions? We've talked
Well,
about
what you visualize, it's a good question. What you visualize are the things that we are the evidences. I mean, well, we know what was well known was the Geiger counter. That gave rise to a click. Of course, it was a tiny...
But that's a click, it's not a particle.
Yeah, that's right. It's not a particle. In fact, that's true even today. I mean, you know, I come to you as a person who's never seen a particle.
Yeah.
I've heard clicks.
Millions and billions of
billions
clicks.
and billions of
But
clicks.
not one particle.
Not one particle. No one. Yeah, I mean, that's somewhere I tell the story of the lady in the audience who said, "Did you ever see an atom?" And I said, "Well, you know, we have objective ways of knowing the properties of atoms. We shine X-ray. Did you ever see an atom?" You know, and eventually I had to admit I never.
Sorry, madam.
Yeah, I never saw an atom, and eventually the only way I could protect myself was to attack. Did you ever see President Clinton? Of course. Well, when did you see him? Were you in Washington? No. He was on television this morning. Television. Did you ever look behind the television set? There's glass. There's a hot wire. All kinds of wires. You mean to say you believe that that's President Clinton?
You believe we went to the moon?
Yeah, same thing. One of the instruments that I liked a lot, and eventually was my PhD thesis, was the cloud chamber. And at the high school, we had a cloud chamber.
Yeah.
Now, in a cloud chamber, invented by a Scottish gentleman where rains were very frequent in Scotland, was a device in which the dust was removed from a box of gas, clean gas, in which there was an alcohol vapor. And then at the pushing of a button, you'd suddenly cool this gas, and the vapor should turn to a liquid and rain. But the rain requires nucleation, requires dust in the air. That's why it doesn't rain in the desert, even if conditions were right, because to form a drop from vapor, you need to have a center on which the drop can nucleate, something on which it can grab. And in this clean box, there's no dust. So you suddenly cool it, and the alcohol vapor wants to condense. There's nothing on which to condense, so nothing happens. But if you're lucky and a particle passes through, one of these invisible particles, the particle is electrically charged, and it knocks the molecules in the gas about, and the molecules get a little excited. And an excited molecule is just right for the alcohol. So the alcohol starts to condense on these excited molecules, forming and growing a drop or droplet. At the right time, you flash a light, and you've rendered the path of the invisible particle visible by a row of drops. I mean, another example of that are the vapor trails of a jet airplane flying very high. You may not see the airplanes too high, but you see the white line in the sky. And you deduce, oh, there goes, you know, the 747 that's going to land at O'Hare Airport at 6:03. And if the white vapor trail made a left turn, you could say, aha, it made a left turn. In the same way, the trails of particles can be tortured by putting in obstacles, and the trail will tell you what the particle did. So that's the cloud chamber, and it was almost as if you were seeing the particle.
Mm-hmm.
So we'd say, oh, there's the particle. What you really were seeing is just a row of tiny drops of alcohol.
Yeah. You wrote, you might find in the primordial universe boring, but to a particle physicist, those were the days.
Yeah.
Such simplicity, such beauty, however mistily visualized in our speculations. Well, give me an idea what your conception, your idea, your picture is of the beginning of the universe. How much do we know? How close are we?
Again, I'm an experimentalist, and I do experiments here at Fermi Lab in which we try to understand the behavior of particles, and we have made a lot of progress in our reductionist attempt to find out what everything is made of and what's made of, and we've come down to things we think may be quite primordial. And then I learn by reading my colleagues who are astrophysicists and cosmologists that these particles are very relevant to their own constructions, because they assure me with their evidence that the world was born in a huge explosion some 10 or 12 billion years ago. And in that explosion, the temperatures were so high that all matter was decomposed into its most primordial components. So that's where the two subjects merge. That's where we can begin. So it becomes, for us now, exciting and wise to understand that other field of cosmology and how it got reduced to the properties of particles and the forces. Then you look at the laws which work so well in our universe now, relativity and quantum theory, and you try to extrapolate these back. But now we're in a domain of temperatures and energies that are beyond anything, way beyond anything we can replicate. At the collisions of Fermi Lab, which are the highest collisions we can organize anywhere on this planet and probably in the solar system, we still we are reproducing what the world was like characteristically, but
you're talking about a tiny fraction of a second
that's
after
right.
the Big Bang.
Yeah, but
those
that,
temperatures
on the scale of time, it's a long time. I mean, it's an infinitesimal fraction of a second, but it's still old compared to the dynamics of the universe. Much, much hotter than 1 million Fermi Labs in the beginning.
Yeah, you're talking about infinite temperature.
Essentially, from anything we can imagine.
Yeah.
Huge temperatures, and therefore conditions of matter we can only hope our equations are okay to extrapolate to, but cannot at all be sure. And we do see that as if we play the history tape backwards and look at the universe getting younger and younger and younger and getting hotter and hotter and more dense, we do see, if we understand it, the complete reduction to something that's beyond anything we know about now. Now we speculate, and so we think, well, maybe at the early universe there was this Higgs phenomenon, which we haven't seen here yet, but which seems to be a clue. I mean, it's a rational explanation of some of the clues, the white car and the bloody glove and the barking dog.
Yeah.
Well, there are clues, and the clues, there are, and Steve Weinberg is one of the clue masters who digs out these clues and tries to fit them together. And Michael Turner, some of the great, cosmologists of today, Steve Hawking, to try to figure out how the thing began. But we get into this mysterious place where time and space are not defined.
No.
And so all we can do, or the way I see it, is to, by listening, is to say, well, there were laws of nature. The laws of nature may not have been the same as the laws we know that explain the phenomenon at Fermi Lab energies, which is, 1 divided by a 1 with 16 zeros of a fraction of a second, an unimaginably small fraction of a second. But at least at Fermi Lab, we understand the properties of matter because we can measure them there. And it's consistent to say that at an earlier phase, things were not so different and extrapolate. But now we're in the region of more philosophy or guesswork.
Guesswork.
Than a science which has factual things. Well, we don't know, but the notion that space and time were not defined comes up at something that happens very close to the beginning. And but the laws of physics might have been there.
Yeah,
sitting there waiting for, waiting in a domain in which time is not defined. In a way, look at this.
No matter, no time, no space.
That's right.
Only the laws of nature.
All the laws of nature. And that's when
Waiting
Willie
for-
says, "Who put the laws of nature there?" And you strangle him, or you send him across the street to the Department of Theology, because I don't know who put the laws of nature there, how they got there.
And let's cut aside for a moment. The laws of nature as the very beginning.
Yes. Well, that's the article of faith of the physicist and the cosmologist, is the laws of nature were there.
How do you visualize
Okay,
that notion?
let me do it this way. Let's look at time. Time has relevance if there's a happening. Our time is measured by the
Movement.
swinging of a pendulum,
Yeah.
or the rotation of the arms on my watch. So time requires happenings. Well, this is not so hard to imagine that you're in a room. Let's do space and time separately. So you're in a room where you have space, but nothing's happening. Absolutely nothing's happening. No heartbeat, no biological process, nothing that is happening.
Nobody noticing something.
Yeah, so time is meaningless. There's no event. So therefore, whether it exists or not doesn't matter. It's not defined because nothing's happening. Now, if we made a model universe that was so simple as one particle, it's unstable, radioactive. So it sits there, again, if it's the only thing in the universe, there's nothing clicking. It sits there stupidly, passing time, but there's no way of measuring it until it spontaneously explodes. Now something's happened. The universe has begun. Something has happened. It has burst apart, and now things are moving. So that's why we'd better invent space at the same time we invent time, because when we invent time, something's happening, and we need space in which that has to happen.
Yeah.
It's wonderful stuff to think about. If it isn't beauty, it's a lot of fun.
Yeah, what's the fun? One singularity, sitting there, doing nothing.
Right.
Not
and out of that,
not being watched.
not being watched.
Because it's the only thing in the universe.
That's right.
It's infinite small.
Yes. Small isn't defined.
So why suddenly it explodes?
Yeah, that's the
the
laws of
thriller.
nature. One of the laws of nature, which works very well today, is radioactivity, is the spontaneous disintegration of an object that is fundamentally unstable. So you have to postulate that the laws of nature are such as that incipient universe, it's not a universe yet, is fundamentally unstable. It's like a boulder perched at the edge of a cliff, so that all you have to do is, have a whim, and it'll push it over. But it's not, and nothing's happening, and then something happens. The universe begins, and you and I are sitting here discussing it after a lot of intermediate steps.
No. Okay. We don't go to the other corner of the street asking about God and theologies. What is your picture? What is your image of what is happening with the universe now? Is it expanding? Although this is the wrong.
No. I think
expression,
it's right. It's expanding. It's expanding. We have these red shifts that Every once in a while, an astronomer stretches the limits of his telescope and finds a new galaxy at the edge of our ability to observe and says this galaxy is 12.7 billion years old. And we say, how can that be? The universe is only 10 billion years old. Well, these are experimentally controversial things which we'll eventually understand. And if you look at these things at the limit of our observation, they're moving very fast away from us. And so we say, well, the reason it's so far away is there was a big bang and everything moved away, and the things that the hardest to see are the ones that are moving so fast that they're the furthest away in this interval of time in which the universe became so old. And so the picture of an expanding universe is a good picture. We don't know the future of this expansion. Will it slow down? I think we're getting to the point where we might be able to soon measure whether its expansion rate is less now than it was at some earlier epoch. That would be a good indicator that it might be slowing down. And then there's the possibility that the expansion can stop and reverse even, what the cosmologists with their fancy language call the big squeeze.
Backwards.
Crunch.
Yeah.
Or whether it will continue to expand but at an ever slower rate, which I think is the consensus of astronomers.
What do you think? What's the most elegant solution for?
Again, I think elegant is, it's a little hard because you can you get enthusiastic about a particular form of elegance, say Harry's elegance, and then John's elegance comes in and it's even more elegant. But you have to give some attention to John so he can explain it. But I think the elegance which says that that's an asymptotic universe. There's an equation, an Einstein equation, which has a constant in it called capital omega. And if capital omega is less than 1, one solution. If it's greater than 1, there's the opposite solution. And if it's exactly 1, we get this asymptotic universe. And there's something elegant about it being exactly 1. And that has to do with our interpretation of dark matter. I think that's knowable. As to the future of the universe is knowable. And that's itself something absolutely incredible. You know what's really the most beautiful of all ideas is that science exists. that this world is subject to science. That's incredible. And that humans have discovered science.
It's a kind of beauty, I imagine, that is sheer beauty to be able to predict, finally, the future of not only our little planet or humankind, but the universe we are living.
Isn't that amazing? Isn't that amazing? I once had a vision when I was the director of this laboratory. We were doing an experiment on the mass of the neutrino.
Your favorite particle.
That's right, my favorite of all particles.
Yeah.
And there was a technique. It's extremely difficult to measure the mass of these things because if they have any mass, it's extremely tiny. But there was a trick.
If they have any.
Yes, they might have 0 mass.
Yeah.
But at one point, the neutrinos were the favorite candidate for closing the universe. You know, because if the neutrinos are around, they're all over us. They're going to get some on me. They were created at the Big Bang, and they're all over the place. There's a density of neutrinos. And if these neutrinos would have an intrinsic mass, rest mass, that would be enough mass to slow down the expansion of the universe and to cause eventually the big crunch. And there was an experiment at Fermi Lab designed to detect this tiny mass. It didn't work, so set your mind. But it could have worked. And I remember once having this incredible epiphany, visiting a graduate student on shift at 3 in the morning on a cold winter night in Chicago suburbs, the wind whistling, and this poor guy had looked like death warmed over. His eyes were bloodshot. It was cold. This little room in which all the apparatus wires had been led to wasn't very comfortable. He was typing in a modem with gloves, which is not easy to do, and complaining bitterly that his colleagues had deserted him and he should have been relieved long ago, but he has to monitor the experiment. We talked about the experiment, and he was, looking at the data. Printer would clack every once in a while and give him an output, and he'd look at it and enter it into his notebook. And we talked for a while, and I commiserated with him. And as I left, I had this feeling, suppose the computer, I had this little fictional continuation where the computer suddenly shows him a result. And he can't believe it, and so he rechecks it. And it keeps saying, mass, neutrino mass. They've got it. And he can't believe it. And suddenly this kid, in these dire circumstances, knows the future of the universe. The infinite future of the universe, of all 1 out of the 5 billion people on this planet, this guy knows the future of the universe. And for the hour or so before he really is sure, and calls up and wakes up his professor. So I got news for you. Can you imagine that? And that can happen in science, and it has happened, not very often, that somebody will come in possession of knowledge that will change the way humans think about themselves forever.
And he is the only one at 3 a.m. in the morning?
Exactly.
Knowing.
The only one.
Tell me, what kind of a feeling was it? Because you have had it.
It's a sexual experience.
When you violate the
Your
parity.
palms sweat. Well, it's happened to me, not with that dramatic insight, but making a discovery. Usually it's always at 3 in the morning.
Your book, The God Particle, has a one-liner. If the universe is the answer, what is the question?
There are only 2 kinds of questions, right? The why questions and the how question. And how is a little more straightforward, because then you feel mechanisms are involved. You need a mechanism. And sometimes the distinction between the 2 questions is fuzzy, because scientists tend to actually avoid the why question. I mean, our job is not why is the universe, but how does it work? Why is more the subject of the people across the street.
Yeah, the churches.
The churches, right. And yet somehow that's not always true. Occasionally you'll find you can ask fruitfully why questions. Why does nature prefer symmetry breaking? And that sort of a wrestling with yourself and that's making nature, that Einstein did that all the time, and sometimes people thought he was religious because he was always wrestling with
the why questions.
The why questions, yeah. As if he was in competition with the Creator to understand the world the Creator made. Hey, the Creator said, "Hey, Einstein, I made this world. Figure out out what I did." And that he...
He didn't have similar feeling, ever.
No. Well, okay, there's
kind
always
of a big boss. Yeah.
That's right. There's a story of Pauli, who goes to heaven, which he did eventually, I assume. And God says, "Pauli, you were such a good scientist. I'll answer any question you want." And so Pauli asked the question in my book, "Why is 137? Yeah. "Oh," said God, "come on." He takes him to the blackboard. He takes a piece of chalk, and he writes out and shows, "See, that's why 137. Pauli says, "Das ist falsch." It's wrong. What's the story? The pleasure of science comes on many levels. The deepest one comes from a recognition that there's a whole. There's a unity, and it covers a large domain, and it's very beautiful. And many examples. The quantum theory is a beautiful example of a synthesis of a huge domain of natural world that we had no inkling of until the end of the 19th century, when the first data came from inside the atom. It was as if, we traveled as far in distance as the space travelers in science fiction traveled to distant worlds. And so this was a entirely new world, the world of the atom. And it took 20 years or so of the best minds in Europe to solve the problem of quantum theory. And then they had a unity. By 1930 or so, when you could step back and look at it, it was an incredibly beautiful, powerful, and even mysterious, and still mysterious, structure. One that has still infinite possibilities for exploration, but so powerful that the world's economies now thrive on our understanding of a quantum theory. Whatever it is, 72.3% of the gross national product of industrial countries is based on our understanding of the quantum theory. I said 73 point whatever because I know that 92.4% of all statistics are invented.
Yeah.
But anyway, it's a huge amount.
Onze economie is voor het overgrote deel gebaseerd op de kwantumtheorie. Het is een vrijdag in Batavia, in de grootste deeltjesversneller ter wereld, en het is een zeer mysterieuze opmerking. Onze economie is gebaseerd op de kwantumtheorie. Want hoeveel van ons begrijpen eigenlijk waar die kwantummechanica over gaat? Ja, begrijpt Lederman zelf wel waar de theorie om draait? Hij vraagt of we niet een stukje zullen paardrijden, daar beneden, in de prairie rond de deeltjesversneller. Zijn lievelingspaard heet Willy. Dat is mogelijk, dat kan, maar laten we eerst horen en zien hoe de beste leraar ter wereld de kwantumtheorie uitlegt. Die theorie die aan de basis staat van onze economie en ons leven. We hebben het nog steeds over schoonheid. Je hoeft het woord niet te noemen om het in elke zin te herkennen. Over de troost later.
More and more as you think about it, you can see quantum effects in everyday phenomena. And so that's the trick, is to try to appeal to everyday phenomenon and take it a little bit below the most obvious level.
The two of us now talking. We're talking about a quantum mechanic event.
Yeah.
What's the interpretation? Two beobachters? Two.
I would start with one of the most spectacular things where you would see this effect is fairly easily seen if you would take some nice fine powder, sprinkle it into water, and with a good strong flashlight, illuminating these little pieces of powder and looking at them, maybe even with a small children's telescope. And you'll see these powder pieces moving in a very erratic way. And the only explanation for that is they're being hit by molecules with an unequal number on one side over another side. So they move because they're small enough so that if 20 more molecules hit them on one side than on the other side, they'll move. And that incoherent motion, that almost Zitterbewegung, was explained by Einstein. It's called Brownian motion, is the existence of molecules, but it's not exactly quantum. That's not enough. The most spectacular quantum effect is when you make toast in the morning, because you plug in the toaster. And you have to wait a few minutes. Maybe you put your hand over it to be assured it's working because it's hot. And then eventually the metal strips turn red. They're glowing. Well, we know if we heat up something, it might glow. But why does it glow red? If you took the theory we understood for many years, the theory of electricity and magnetism, any simple explanation of theory, the energy you put into this wire should be blue incandescent, blue-white. Instead, it's a dull red. And in 1900, Mr. Planck, trying to understand this problem, was the first one to say that energy must come in lumps, in pieces. So much so that when you heat up a metal, the energy, it's too costly to make white light. You have to make red light. There's a kind of a metaphor in this that comes from, let's see if I can get it right. Let's say you have a famous pianist that's going to play at the Symphony Hall. But people can pay money and go in, but there are no chairs. They can stand anywhere. Well, all of a sudden you see a huge collection of people over on the left side and in the front. Why? They want to watch his hands. Those are the favorites. Everyone is standing there. The rest of the auditorium is vacant. That's one way of looking at nature, and that would be equivalent to the classical theory in which this metal would glow white with energy.
But it doesn't.
It doesn't. And the metaphor is now you have seats, and people can only have one person in one seat. And there is no longer accumulation there, but people are spread out and distributed over the auditorium. Maybe more in the front because the seats are better there, or less in the front because they're too expensive. So there's a balance and you get a distribution. That's the red light. The seats, it's a metaphor. Metaphors tend to be very crude. Mm-hmm. But Planck found that by quantizing the way energy is emitted from this hot wire, by making it in lumps, he could explain the data, which his colleagues at the University of Berlin were getting from hot wires. And that was the beginning. And then Einstein advanced that idea of quantum theory, because what came out of Einstein's interpretation of experiments and Planck's interpretation of experiments is that light itself, the kind of light that affects our eyes, that comes from the sun and from light bulbs, comes in streams of particles. You know, if the light is weak, then you have few particles. If the light is strong, you have many particles. Now this gives rise to a major crisis. You're walking down a principal street, say somewhere in Amsterdam, and there's a store window. And someone in the store window is working with a mannequin. And you see the man in the store window, and he sees you. You're brightly illuminated. But you see something else. You see an image of yourself in the window. Dim, but it's there. It's enough for you to admire yourself. Now, how does that play when we think of light as a stream of particles? So sunlight illuminates the tip of your nose. A photon, a particle of light, heads for the store window. Sometimes it goes through because the man in the window sees you, and sometimes it's reflected because you see yourself. When is it reflected, and when does it go through? If you do the numbers more carefully, it turns out about 96% of the photons go through the window and 4% reflect. Are these photons that reflected any different from the ones that went through? Quickly, you're led to the conclusion they're all the same. So what determines whether a photon will go through the window or be reflected? The answer, which so shocked Einstein that he got off the train of quantum mechanics and refused to believe it, the answer was, it's a random process. Who put it that way? Yes, Einstein put it that way. He said, I cannot believe that God plays dice. But it's exactly what God or nature does. It says, okay, here goes a photon, rolls the dice. If it's anywhere from 1 to 96, the photon goes through. But if it's from 97 to 100, the photon is reflected. Every process in nature has this probabilistic feature. And that's the shock of quantum mechanics, and that's what I take a year to explain to these students, and we work on this and many other examples. But it's a shocking thing. Quantum mechanics is the largest change that humans have made in their understanding of the world since science began, in my opinion. And we still don't understand it because Einstein's deepest objections have never been answered. And they're the subject of continuing research.
You talk about it with a mixture of awe and wonder.
Yeah, and joy.
And joy.
Yeah, because it's really something to have an enormous privilege to be able to be even an observer in these discussions. Auditor. Quantum theory is a weird theory. And the more we track down this old argument between Bohr and Einstein, and we trace it and we go through Bell's theorem and we look at the experimental consequences of that, it's weird. And I'm hoping that it would be nice if somebody finds a better theory that would be more comprehensible. Mm-hmm. But it may be not. We were talking about poodles.
Yeah.
Poodles are smart dogs. Now, my poodle has no trouble with algebra, but I'm sure that she would never master calculus. You know, just no way her brain is going to get to calculus. And it may be that we're like that with the quantum. Maybe our world is such that our brains are not capable of reaching that understanding. It's not only language which we hide behind, our inability to have the richness of language. It may be deeper than that. It may be as deep as the notion of a poodle doing calculus.
In the moment you find the equation, the final law of nature, you write it down. And at that very moment you realize that you don't understand it. You know it's the final law, but you don't understand. Is this a possibility?
Yes. It's a possibility. You can stumble on this thing through manipulating formulas and so on. And in some sense, that's what happened with the quantum theory. There was a lot of accidents in the development of the quantum theory. Here is Schrödinger wrote down his equation, which we use every day in this laboratory, and he didn't understand what it meant. He thought he understood it until it was pointed out to him that it's not what he thought. It was something else. And I don't remember the exact quote, but he said, "Ach, if I knew that's what it meant, I never would have written it down." And he was another one who rebelled against this part of this quantum theory, which we call spooky. And he's the author of Schrödinger's cat, one of these dilemmas of Schrödinger of quantum theory, but not even the most difficult one. So that's a theory which we don't understand yet. Now, this is we could be right and wrong. We could be right that we'll never understand it because we don't really have, it's not within the realm of human cognition in the same sense as the silly business of the poodle. But we may be, again, we have a certain amount of arrogance and self-confidence and optimism. And I happen to believe that we will understand this. That somebody, maybe some kid now suffering from some primary school which is not teaching him well, will survive that terrible experience.
At 3 a.m. in the morning?
At 3 a.m. in the morning, he'll say Eureka or whatever it is in Swahili or whatever the language is this person, he or she uses, and he will understand quantum theory. And he'll be the only person at 3 in the morning out of 5 billion, or by that time 10 billion people, who understands quantum theory, until he calls up his professor, and his professor then commits him to an insane asylum. It can't be like that. Maybe some of those have already been. It's sort of tragic that we had at this laboratory a young lady who grew up in a dirt floor village in the Amazon, Indian lady. And by some miracle, a teacher in this little village recognized talent, and somehow she got to a school, and from then on went through university and became an astrophysicist with a PhD. Well, how many people like that are lost? Never get discovered. A village in Africa or Indonesia, somewhere in the world. Because the fraction of people that live where they could be rescued, I'm talking about giftedness, must be small. Must be 3 or 4 times as many people who would never be discovered. That would be a loss. And somewhere out there, there's some child who can cure senility, and if we don't find him soon, I'm going to be in trouble.
You'll be in big trouble.
Big trouble, right. So I want to appeal, make a general appeal, find that child. And whether it's the cure of senility or cancer or...
You still remember what I asked 2 minutes ago? Or?
No.
You didn't?
Certainly not.
Steven Weinberg wrote, "As we look beneath the surface of things, we find more and more beauty. We would not accept any theory as final unless it were beautiful." Do you agree that you will find more and more beauty? And if you find more and more beauty, how do you define it?
The defining of beauty is a little bit of a hopeless task. But I think what Weinberg finds, I think there's universal agreement. There have been many stories in which deep thinkers, have said, this theory is beautiful, it must be right. Einstein, when he was told that his theory of relativity was confirmed by Eddington's expedition, he said, of course. How could it be otherwise? He believed in it because it was so beautiful to him. And many examples, Dirac, total faith in a theory because mathematically it was so beautiful.
The electron.
Conceptually, that's right. It had to be true. And we've come a long way with that. That goes back to the Greek conception of science, that there must be a satisfying, overarching principle by which this complex world works. And the Greeks knew about beauty.
Is beauty in this way similar to ordering?
Ordering?
Yeah.
Yeah.
Isn't that one of, for most people and scientists, one of the deepest sources of consolation and beauty? Without even understanding what they are seeing.
I would think order is synonymous with beauty. The order is the beauty. The fact that it's ordered. That's where, when you imply that mathematics is an invention of the human mind, and the fact somehow nature seems to love mathematics very much. Yeah. I do that with my class. I throw a piece of chalk across the front of the classroom. I say, you know what that is? It's a parabola. My God, a parabola. How could nature know? Something invented by an Egyptian or a Mesopotamian, 4,000 years ago, that this would be exactly what a piece of chalk would do when I throw it across. That's order. That's the wonder, that nature is so orderly. I think order is is the beauty in science, is that we found order.
More and more and
More and more, right. The Greeks said the world would be simple. Offhand, they had to prove it. And the history of science has continuously confirmed that idea.
Mm-hmm.
Look at Newtonian mechanics and cosmology. Here was Newton with equations you can put on a T-shirt. F equals ma, and F equals g m1 m2 over r squared.
Yeah.
Gravity and laws of motion, an incredible amount of the world became clear. Things which you had thought would have no connection. An apple falls from a tree. The tide goes up in Canada.
And are connected.
All connected. And Halley's Comet appears exactly when it should, according to the almanacs. All connected. Well, that's powerful confirmation of the Greek idea of simplicity and parsimony. A simple idea can explain so much of the world. It didn't explain all of the world. And that's why we needed relativity. For those parts of the world in which velocities were huge compared to ordinary velocities of bullets and cannon shells and the flight of birds and bees. And it didn't explain the behavior of the atom. But now we have relativity and we have quantum theory. Two pillars of our modern understanding. Unfortunately, these two pillars haven't talked to each other. They're independent things, and so one of the problems of modern theoretical physics is to see whether these two have some common unifying, overarching principle. But
They have.
They have.
Superstrings.
That's right. But so
Have
that's
they?
well, you know, that's a possibility. But we deserve to have confidence in the belief of beauty and simplicity. That's what we were talking about, because we have so many examples in which a previously incomprehensible, disordered, complex set of phenomenon suddenly became simple, coherent, and beautiful, because you found the right way to look at them.
We just had lunch. I said to you, I want to talk about the beauty of science, and you said, well, let's talk also about the science of beauty.
I didn't say let's talk about it. I said there exists the possibility of talking about
Yeah,
it.
and so what do we know about it, the science of beauty?
Well, my guess is that's, if you really want to stay to the scientific part, it's invested in neurophysiology and computer science. I mean, somehow the mixture of those things, which then would try to analyze, you know, where the brain receives information of this kind and how it digests it. And the whole business of a sense of humor. Where did that enter the stream of evolution? So that
Why?
Yeah, why? Yeah.
Yeah.
What's the purpose of humor? Is that we know in today's world you need humor to survive, and that's probably been true for modern society in, say, the last few hundred years, or maybe even 1,000 years. But way back, when you were defending yourself against dinosaurs,
Yeah, humor? No.
seems to me you needed to have a hard business sense and very practical things. But humor and, yeah. And when did we start to stare at sunsets and say, how beautiful, look at all that? Maybe it was only after pollution made the sky so red.
Yeah, but laughter, having fun.
Yeah.
How important is humor? You said it's a kind of survival
Yeah,
instrument.
I think so. I think if you can't, I mean, Shakespeare knew that very well. If you can't laugh at yourself at some point, you might, I don't know, it's a release to step back and see the humor of a situation. But how this helped you survive in earlier times was beyond, I mean, it's what I call above my salary level. some other people could probably make wise remarks on this, people who've thought about it deeply for a long time. But, there'll be a tremendous payoff when we begin to understand the neurological basis of aesthetics. Because then, we could package all kinds of pleasures. I actually wrote a story once, which was never published, inspired by people who did experiments by planting small wires in the brains of a monkey and putting electrical voltages on these wires, and eventually finding a place where the small electricity made the monkey smile, or the equivalent of a smile. And it was clearly a pleasure center. And eventually they moved it around and maximized the effect. And they attached the electricity to a pedal with a strong spring. So the monkey had to push hard on the pedal and gave himself this pleasure. And then he pushed on the pedal as hard as he could. And then they tried to measure this by bringing him some delicious, monkey food, foie gras à la monkey or something. And the monkey was not interested in the food. They brought him a beautiful female monkey, and in heat, no interest. He was pushing on that pedal until with his last bit of strength, before he fainted away. He was one more. So I thought this was a great, the end of human ambition.
Yeah.
And I called it the helmet, and you have all these wires, and then you don't want to do anything, right? Because you can replicate it. The pleasure of composing a symphony, or the pleasure of writing a book, or the pleasure of winning a woman, and this is 3.2 volts located at the following coordinates, and then it's even better. I thought it was very depressing. I said, once we can technologically solve that problem, then it's the end of all innovation. And then I realized it's kind of nonsense, because what gives me pleasure is not my own brain, but Mozart's brain. And others like that, the creators who've exposed things to me. And that's more subtle than simply looking around for voltages in my brain. But ultimately, the brain will be the place where, I guess, many of the successful biologists are now going to the brain as the great frontier.
It's remarkable. If I ask people about Beauty and Consolation, they come up with paintings, music. Mm-hmm. Nobody comes up with laughter, fun, or sex.
Yes.
Isn't it a little bit ridiculous? Because
the sex, no, because people tend to be awkward about sex, and but you're right. That's absolutely right. And humor is, to me, humor is the essence of creativity. I was on a television program with a guy who was very humorous. He was he made his reputation as a comedian, and he was interviewing me and a person from an organization known as Mensa. I don't know if it's an international organization, but it's an organization of people with high IQ. IQ being a measurement, presumably a measurement of intelligence. And he was so awestruck at this, what I thought, very ordinary lady who seems to have had on a high IQ, and cracking jokes and illustrating something which IQ never measures, which is humor and creativity. Yeah. I mean, if you look at the people with high IQ, the question of their creativity, I mean, I don't know the numbers, but my guess is you don't find extraordinarily creativity in people of high IQ. And it's creativity that's much more interesting.
Yeah, without humor, without sense of humor.
Yeah,
What would your life be like?
That's right. It would be unimaginable. And yet there are humorless people that just go around. They have no humor. Humor might be an accidental byproduct of inventiveness. Here's, somehow this Darwinian supervisor of our futures says, well, if I want this species to survive, I have to make them more creative. And so you do things somewhere up here to be more creative. A few more threads, a few more neurons in some complex way. I don't know what I'm talking about, incidentally. I want to make sure I haven't the slightest idea what I'm talking about.
I don't think we have a real concept of, for instance, beauty. Consolation, perhaps.
Yes.
The sense of beauty. Or
Yeah. And yet it's very common, right? I mean, in fact,
it's something like
humor is incredibly international.
Yeah.
I mean, across cultural lines. I mean, there are clearly some differences, but I've visited my anthropologist daughter in a mountaintop in New Guinea, and I found humor there which I could recognize. Came right from New York City.
What kind of humor?
Well,
Do you remember?
yeah, humor about your own circumstances, you know, your own limitations, self-mocking humor among these people who are, you know, maybe 20 years away from the Stone Age, 30 years, something like that. You know, making fun of themselves and imaginary situations which were humorous and laughing together. So, and that's very universal. It must be fundamental. Maybe you're inspiring me to take a course or find an expert somewhere, and I'll trade him for quantum mechanics for humor, for the
quantum mechanics of humor. Yeah.
Oh, that's
like
another
that.
thing.
How did you feel? You're coming into the Stockholm Theatre. You won the Nobel Prize.
Yeah. Wow.
Huh?
I felt I kept.
What sense of humor did you have?
I said, I'm going to recommend this to all my friends. I said, this is great. And I also have the feeling often I'm getting away with this. You know, they really believe me. I'm dressed in this monkey suit, and there's the king and so on, and they really think I'm a great scientist. That's so silly of them. They don't really know. It's a big party, and it's ritual. I like the ritual. I think I really do believe that, you know, there's a pleasure in this, a gratification in this, especially when I can get that close to the Queen, and she's beautiful. Actually, she's just the image of what every little boy thinks of as a queen. She is. She's quite young. I think in '88, when I first saw her, she was 30-something, 34. So she can't be that much older. She's very charming. And she's beautiful in a deep way, that, you know, a way of personality. It's mixed in with her beauty. I'm going there again in December. I'm going to see her. I'll say hi, Sylvia. She'll say hi, Leon. I think. But it's a great. It's an amazing fantasy that something like this can happen. You know, and once upon a time in a strange land, the king and queen, you know, put everyone in the country to work to make a party. For me, the whole country, for its Thanksgiving and 4th of July and Christmas and New Year's, all in one. For Sweden.
Kind of whimsical.
Yeah, and the whole thing is whimsical, and it's I tried. I had to give a 3-minute talk at this big banquet, a huge banquet, an intimate dinner for 1,500 people in the town hall. And I tried to, in 3 minutes, not only explain what our contribution was, but to make it as funny as I could. And my wife, who listens to all my jokes, and told them to the king, and so there was a division of effort in that she made the king giggle. I saw him giggling, you know, continuously, and in return, the queen made me drool. I guess it's just a grown-up version of of a children's birthday party. You know, when your child is 1 year old or 2 years old and you make a party thoughtfully, you know, designed for the child and not for all the guests, and the child is filled with the fantasy of the gifts and the fuss about the child and so on. This is just a grown-up version of that.
Yeah. Grown up.
Well, sort of grown up.
Sort of. I quote Eliot out of the East Coca. As we grow older, the world becomes stranger, the pattern more complicated of death and living. Not the intense moment isolated, with no before and after, but a lifetime burning in every moment. Ha! That's something. Huh?
Could you read it faster?
I'll ask Stephen
No.
Gould.
Right.
But now you're growing somewhat older,
Yeah, somewhat, right.
entering senility. I talked to Ed Whittam, and he said I was an agnostic from the very beginning. God or a moral God, no deal. Did you have any projection of God, the Messiah?
I think when I was young, I did have when I was very young, it was a refuge from fear. If I worried about the fact that my parents hadn't come home and it was late and maybe something happened to them, I did say a few words just in case it would do some good. But I grew out of that after a while. And then for long periods didn't think about it at all. And I was tolerant. I mean, I didn't mind other people being religious. That's fine with me. I was somewhat amused by people whose religion was so obvious that they would, you know, you could recognize them on the street, either because of their frocks or their white collars or whatever it was. Now I get very concerned when I see that, because so much of religion is fundamentalism, and I think fundamentalism is a danger to survival of rational society. But I came back in some sense, not really come back. Once I got to understand what we know about the universe, the world, both in the ultra small and in the ultra large and its origins, I realized that there's always going to be a perpetual mystery. That whereas 20 years ago, when you were asked the question, you might say, well, you know, you have to go across the street to the Department of Theology. I can't answer it. Now, we're better at it. We can answer that particular question. But ultimately, if this obnoxious kid keeps asking questions, we'll come to a point where we have to send them across the street. And I think that'll always be so.
I remember I come up with Stephen Weinberg. Do you know him well? Or?
Yeah.
He wrote it would be wonderful to find in the laws of nature a plan prepared by a concerned creator in which human beings played some special role. And he writes, I find sadness in doubting that we will. Do you share this sadness?
No. No. Why should I be sad if there's something we that's unknowable? It's unknowable. It's unknowable. There's also two parts of that. Is it something I will never know, or is it something I, as a member of the human race, will never know? And there are a lot of things I'm comfortable with not knowing. I'm comfortable with not knowing what the stock market will do tomorrow. Doesn't bother me. And so many things like that. There are complex things in this world. Who's going to be the next president? I'd like it to be a good person. But I'm not particularly saddened by the fact that I don't know this, or that there are things in the world we might not know ever. Maybe like some of these things that have to do with how the mechanics of the early universe, which we may never know. As long as the overall scheme becomes clear. I would be very sad if we were blocked from access to the overall scheme. So Now, what did he say again?
It would be wonderful to find in the laws
Oh,
of
humans.
nature
Yes, it's the
a plan prepared
Yeah.
by a concerned creator in which human beings played some special role.
yeah.
I find sadness in doubting that we will.
Yeah, that's an interesting side effect. I mean, the whole business of whether we're special is an interesting one. It's not really physics, but that's okay. It's sort of a little bit outside of science.
Mhm.
There's the anthropic principle. You can have a lot of fun with that. It's not science, but it's interesting.
It's all made for us to emerge in evolution.
That's right.
The only creatures in the universe.
Right. And it even resonates with some of these more speculative aspects of quantum theory, this business of subjectivity and human effects on observation. But I strongly believe that we're an accident of the chemistry and physics of the world, and that we're not special. So I guess I'm in the Copernican school, which says man doesn't deserve to be in the middle of the universe. You know, he just inhabits a tiny speck in a nondescript solar system, part of a mediocre galaxy somewhere in the cluster of galaxies of not much, remarkable aspects. And probably here and there are other specks which are inhabited, probably. But that somehow we're involved in the creation, I can't believe. I think we're just...
Side effects of.
Yeah, just a
leftovers.
spin-off, if you like, an accident of chemistry and biology. And that's what the anthropic principle marvels at, the fact that the mass of the electron were 1% different from what it is, we wouldn't exist. And it's worth remarking on that.
How consoling is it? I mean, being totally alone in the universe. We came into being by an accident.
Yeah.
A kind of leftover of neutrinos. Yeah.
Leftover, in one sense, of the matter, the asymmetry between matter and antimatter. That's part of our accidental heritage, and the fact that the oceans were the way they were, and out of these oceans, accumulated complex proteins evolved, and out of the sea we crawled, along with the other organic ooze that took place, and we evolved. It took us plenty of time, 4 or 5 billion years. And in that time, lots of miraculous things could happen, because out of the billions and billions and billions of processes, one of them was bound to create a DNA of some kind. And here we are. That's not... I'm not disturbed by that. I'm not consoled by it or disturbed by it. I think that's probably the way it is. Are we alone in the universe? That's another question. It may be, an interesting cockroach society, or, you can pick your own science fiction scenarios for finding other beings. My guess is we have other beings, just because of the same accident could happen again. If it happened once, it could happen again in a slightly different way. So that in some other planet, some other place, we have, say, only Republicans or Democrats
No.
or
Please,
communists. Beware, be careful, don't go too far. And so I'm not... I'm not sure that's relevant to being consoled or not.
Do you understand why for so many people an afterlife, immortality, eternity, is a kind of consolation, of ultimate consolation.
Oh, sure, that's not so hard. I mean, it's very difficult to appreciate the notion that you will no longer exist. You know, that's something that most humans, you know, can't imagine. And therefore, some continuation of your consciousness would be a consolation. And somebody offered it to me, whether he wore a black cassock or a white collar or a long black robe, you know, I would probably accept this. It was a deal. I could trust him. I would invest in someone who promised me infinite consciousness.
Infinite consciousness.
Right. But, you know, I'm sort of skeptical. So I think, in fact, that's not in the cards. And one could feel bitterness. You know, how could you do this to me? How could you bring me up to this point where I'm, you know, so powerful? I can imagine, like, what could be worse than Beethoven going deaf? You know, or some great scientist suddenly stricken by Alzheimer's disease. But being conscious of it before you pass into some realm where it's all confused and nothing matters. It must be terrible things to happen to people. Lose your power of, you know, awareness. So, yeah, so the notion of an afterlife or of continuation in any form must be very, you know, appealing to anybody.
It's appealing for you?
No, because I just don't believe in it. I think at some point there will be, you know, whatever you want to call it. Since I sleep very well most of the time, it would be like sleep.
Are you more and more afraid of dying, or
No,
less and less?
neither. Neither less, or more. Maybe less, maybe somewhat less. I think when you're young and you do funny things like join the army or climb some high mountain and so on, and worry about it because there's so many things you still want to experience. Well, I have no complaints. So I'm not worried anymore. I've really been very lucky. And I can't imagine, you know, being transported to some mysterious heaven where things are much better off than they are now. For me, that would be unimaginable. You know, you could tempt me with, let's see, who? Sophia Loren, Gina Lollobrigida.
For more than 10 years? Or for the month?
Yeah, no way, no. It'd have to be, you'd have to promise variety, continue.
Yeah, what would the angels have to sing for us to be eternally blessed?
Yeah, I think it's, to me, it's too much.
It's the real punishment, being immortal, even with Sophia Loren.
Yeah, I would be her punishment. Is that an old joke?
Yeah.